x and y, when we understand that they can be put into polar, we are going to use this point. So let me remove this part here and say, so the coordinates of the point P, now the same coordinates are x is r cos B and y is r sine B. Right, I can still keep rotating anti-clockwise. By the way, this is the starting point where theta is 0. We call it the positive axis. This is the initial line, actually. This is our initial line. So because theta is a measurement of the angle between the positive x-axis, which is from the initial line going to P as it is. So if I have another point here, from here, let me say it is here. One thing that we understand according to our construction, this is still going to be r, because any point from this point to the circumference is r. But if I call this point Q, it will also assume the x values, x and y, likewise, same here. But however, the angle of inclination from the positive axis, which is the initial line, to the line P is this angle here that I'm choosing to call, this is angle here, I'm choosing to call it A. I'm choosing to call it A. So if I follow the same order that we have here, that this is r cos B, r sine B, it automatically tells us by following the same order, without doing it again, that this is going to be r sine, this is going to be r cos A, and then r sine A. That's the coordinates here of Q. And if we connect the triangle that we've made, we've got another line which we call QP. We've got another line QP. So in this case, we now have a triangle that we've created, and this triangle is actually triangle OQP. Is OQP here. And the angle between OP and, okay, let me just write that again. And the angle between the line OP and the line OQ is simply A minus B. We understand that to find, maybe I should use this way, better way of doing it in geometry is to say the angle and the angle QOP, is equal to A minus B, because simply the distance from here to the line P is A, and the distance from, and the angle from this point to the line OP is also B. So this is going to be just A minus B. All right. So applying the distance formula of the line QP now gives us QP squared is, since we know from the formula of distance, generally the first formula of distance we know is d squared is equal to what? Is equal to x1 minus x2 squared plus y1 minus y2 squared. You can also say x2 minus x1. It doesn't really matter in this case. So it follows to say QP squared is going to be equal to the x values that we want, which is r cos A minus r cos B squared plus r sine A minus r sine B squared. You will find that this proof can be changed and put r as 1 because it's going to cancel out anyway. And if we quickly expand this, let me just write it here where there's space. QP squared is actually equal to r squared cos squared A minus 2r squared cos A cos B plus r squared cos squared B, and expanding the second bracket will give me r squared sine squared A minus, I'm going to briefly write it here, 2 r squared sine A sine B, then plus r squared sine squared B. So we understand again that we have got the Pythagoras theorem that says cos squared theta plus sine squared theta is equal to 1. That's the Pythagoras theorem anyway, which can be written as x squared plus y squared is equal to r squared. We are going to rearrange this in that order that we understand. So that gives us qp squared is equal to, I'm going to arrange cos A together with sine squared A. So I'm going to have r squared in brackets and then say cos squared A plus sine squared A. I'm also going to group cos squared B together with sine squared B. So that reads r squared cos squared B plus sine squared B. Then obviously I'm left with minus cos A cos B, and then I'm also left with minus, so I'm also left with minus 2r squared cos A cos B, and then I'll just write it below here as well as minus 2r squared sine A sine B. And if we keep on checking, this amounts to 1. It's an identity, Pythagoras theorem, 1. So all this is 1, which leaves us with r squared plus r squared minus 2r squared cos A cos B minus 2r squared sine A sine B. Let us just simplify it quickly here as 2r squared minus 2r squared cos A cos B minus 2r squared sine A sine B. I will call this my equation number 1. Yeah. So the same distance, I'm going to write the same distance again using the cosine formula. Well, many of you, cosine rule. Cosine rule actually is the scalar product that says A dot B is equal to the modulus of A divided times the modulus of B cos theta. So the cosine rule can be simplified to what you understand more as A squared is equal to B squared plus C squared minus 2BC cos A. Is the same thing for those that do vectors in advanced vector calculus. You normally use this one. All right. If you follow my videos, you'll see I have proven that they are the same at some point in time as well. So we are going to have QP squared being written as these two sides here, which is r squared plus r squared minus 2 r squared cos the angle in between this is A minus B. These two formulas, I'll call this one equation number 2. These two formulas, they mean the same thing. They are calculating the distance QP squared. So we can actually equate them to each other so that we are left with 2r squared minus 2r squared, because these two add up to 2r squared. Then cos A minus B is equal to 2r squared minus 2r squared cos A cos B minus 2r squared sine A sine B. You will realize that a lot of things are cancelling out here. So I'm going to make space here. What cancels out is the r squared are gone. This cancels out with this, and the r squared as well gets cancelled out, and the minus 2 throughout gets cancelled out, such that on the left hand side we are left with cos A minus B. On the right hand side, if we cancel out a negative, this becomes plus. Is okay, let me just, probably it's not easy to see for some. So after I've cancelled out everything here, there is minus 2r squared cos A minus B is equal to minus 2r squared cos A cos B minus 2r squared sine A sine B. So I've got to divide both sides by minus 2r squared, everything. Then what is left is cos A minus B is equal to cos A cos B plus, because I'm dividing with a negative here, sine A sine B as required. Proved. So the expansion of cos A minus B is used as cos A cos B plus sine A sine B. Then this is proved as required. All right.